Well, let's go ahead and get started. We've got hopefully Colorado joining us. We talked to them this morning and they're planning on it, so they might just be having a little bit of trouble connecting or something may have come up. So we'll go ahead because I know you guys have to change periods pretty soon, so we'll go ahead and get started. Um,
Okay.
when they do join in, one of the things that we have to just remember is because there are two different sites, we either have to have our microphone muted or be able to kind of be quiet so that everybody can hear. Because if somebody's in the back rustling papers, then the other side can hear you as well. But as long as they're not here, we should be good to go with your microphone unmuted. So like I said, my name is Allie Depew, and today we're going to be talking a lot about solar energy. So we've got the sun, obviously solar energy. Solar energy comes from the sun. And one of the things I always like to start off by saying is, well, what do you know about solar energy? Why are you telling us about solar energy, and what are your qualifications? And so one of the things that I do is, besides teaching about solar energy and teaching, I'm also an energy auditor. And so what I do is I go into people's homes and businesses and I take a look and I say, okay, oh, there we go. Is that Colorado?
Hi, Colorado.
Hello, welcome. We just got started. My name is Allie Depew, and we're just getting going on our conversation about solar photovoltaic. And I was just telling the other school that now that we have multiple schools, one of the best things to do is to have our microphones muted so that everybody can hear. And then I will be asking lots of questions, and so I will have you unmute your microphone. So you might want to keep it handy right there to mute and unmute. So please, if you have a question throughout the presentation as well, raise your hand, and then I will see who is. Oh, I see one in the back over there. I got you. So we can. What's your question?
I have a question. I'm sorry, I don't have a question.
Okay, you were just practicing. Very good. Good practice.
Yes.
Excellent practicing. And I don't know where Colorado went. They were here a second ago, and now they're not. So, like I said, we're going to go ahead and keep going. So, okay, so this side. So I go into people's houses. I take a look at how efficient their houses are, and then I make recommendations for how people can make their homes or their businesses more efficient. And sometimes that includes the use of solar panels. And so I work with a company known a solar plexus out of Missoula, Montana, which is where I'm located. And what they do is they do the install for the solar panels, and then they have me do some education, like I'm doing right now. So first of all, let's talk about a little bit about the sun. Anybody want to guess how much energy is coming from the sun at any given moment?
A lot.
Very good, exactly right. How about a number that looks something like this? That's a ton. So it's 3.8 octillion, or 3.8 times 10 to the 26, and we're talking about watts or joules per second. So that's a lot of energy that is coming from the sun, and this is something that is coming from the sun at any given point. All right, so when we're talking about energy and how much energy is coming from the sun, who is this wonderful fellow behind me?
Einstein.
Einstein, in what equation? Who can tell me what is that famous Einstein equation?
E equals MC squared.
E equals mc squared. And who wants to tell me what E, m, and c squared are?
E is energy.
E is energy.
M is
E
mass.
is energy. Good. What is the m?
Mass.
Mass. And what is the c squared?
Speed of light in a vacuum.
Speed of light in a vacuum. Very, very good. Okay, so we have E equals mc squared. So when we're thinking about that, when we're thinking about Einstein, what he's saying is that, okay, well, energy, then we start getting into the laws of thermodynamics, and is one of those thermodynamic laws, as you might know, is that energy cannot be created nor destroyed. And so what he is saying is that energy can change form, and it can go from one place to another. So what's really important when we start thinking about that with sun, so basically that's saying, okay, well, the sun has energy. How can I change that energy into electrical energy. And that's when we start thinking about photovoltaic. Now, photovoltaic is a little bit different from some of the other solar thermals, and we'll talk, or solar energies, and we'll talk about that in a minute. First of all, here's our world. We use about 1/10,000th of the energy that is sent to us on a daily basis from the sun. So what that tells me is that we have quite a bit of room left for improvement or energy from the sun that we could be utilizing to make energy for our homes, to power our cars, to power our factories, all of those things. So we look at that and we think about it. Okay, so the world energy consumption right now is approximately 474 times 10 to the 18th. Approximately 2% of the energy from the sun reaches Earth. And so what we end up getting is about 7.6 times 10 to the 24th watts that are reaching. Which of these two numbers is larger?
The second one.
Second one, this one. So if we take the difference between this one and this one, that's about the amount of energy that we have to work with from the sun, which is quite substantial. Okay, just to give you an idea of how substantial that is that if we were to say use the sun's energy to grill hamburgers, we could grill, this is a hard one to go with, 2 sextillion, 615 quintillion, 472 quadrillion, 127 trillion, 519 billion, 908 million, 987,000, oh, and I got off again, anyhow, per hour. So that's a lot of hamburgers, just as a funny way to think about how much energy is coming to the earth. So you could grill that many hamburgers in an hour from the sun. Pretty incredible, if we were harnessing it all in a way that was appropriate. Okay, so let's talk a little bit about those different types of solar energy that we have. So there is the photovoltaic, and these are solar panels. Raise your hand if you ever seen a solar panel on a building, a house, maybe you even have some on your house. What do you guys think? Yay! Awesome. Does anybody have solar panels on their house?
Not yet.
Anybody have them on at the school?
No.
No. So a lot
No.
of the things one of the trends that we're seeing is a lot of schools are starting to put solar panels on the roofs of their schools, and we're going to take a look at one school that was able to do that. They got a grant and were able to put solar panels on their school. So another way you use solar energy is called solar thermal, and solar thermal is using the sun's heat to create hot water. Now there's a couple different ways that we can do that. There's a passive and an active solar, and I'll talk a little bit about that with this picture, but basically what it does is these are super vacuum insulated tubes that when the sun hits it, the water heats up very warm. It's actually not even the water that's in these, but a chemical that's going to heat up that's then going to go ahead through a coil and heat the water. So it's a very effective method of heating up water. In fact, it's so effective that places like Hawaii have now changed their building codes. So if you do any renovation to your house, or if you build a new house, you are required by the building code, to put solar hot water on your roof. Energy, as you can imagine, in Hawaii is extremely expensive because, well, how do they get that energy besides the sun? Do you guys know? Any guesses?
Fuel.
Say it again.
They said fuel.
Well, fuel, but how does the fuel get there?
It's in the ground.
Not in the ground.
Barges.
Barges, gigantic barges. Exactly. They've got to ship that fuel to Hawaii. So it is outrageous. It is up to 4 times as expensive for energy in Hawaii. Hello, Colorado again. As it is in some other places. And so you have to think about all of that. And so when you start thinking about that and you think about the savings that something like solar hot water could do in a place like Hawaii also, when you think about that somebody had to, let's say we're working with coal, somebody had to mine the coal, somebody had to transport the coal to the ocean, then they had to get it on a barge to transport it to Hawaii. Suddenly, that's a lot of energy used just in getting the coal to Hawaii. So what we're seeing is a lot of alternative uses of the sun to help reduce some of our more traditional fuels. So then I said we were going to talk a little bit about, I was going to tell you a little bit about passive solar. Anybody want to take a guess what passive solar means when I say passive solar?
Non-aggressive.
Okay, it's not aggressive solar. Perfect. It's not going to punch you. Now, so passive solar, what we're talking about with passive solar is solar that doesn't require any machines or other energy in order to make it work. So this is a passive house. What this house is designed to do is it's super insulated. It has windows that are strategically placed on this house. So it's going to use the sun's energy, and it's going to bring the heat from the sun into the house. And this house will be warmed by the sun, hopefully throughout the year, despite where this house is located. Building science allows us to do that. It's not done very often, but the technology and the science is there to do it. And so this is what we call a passive house. Anybody want to think of another way that we use the sun's energy passively? What do you think? No guesses? How about drying your clothes with just putting them on a clothesline outside? That would be using solar energy in a passive form. There's another way that you can do solar hot water without using, that is not an active form, but simply heating up water. In fact, some of the people in Hawaii, their solution is they simply run black tubing along their roof that their water goes through, heats the water in that respect, and then they use it directly from there. So it's not even, it's pretty cool. There's no pumps, there's no anything. It just moves through. So there's a lot of different ways that we can use solar energy. There's also another one is the passive solar cookers. It's basically a box that has a lot of mirrors and a lot of reflection, and you can cook food using the sun's energy. You can get temperatures up to around 400 degrees, and we're seeing a lot of that used in developing countries, especially places that don't have access to electricity and rely on things like wood fires in order to cook their meals. And so we're seeing a lot of wonderful things come out of that. Okay, enough about that. Let's go ahead and talk a little bit about solar photovoltaic. So right here, this is actually you can kind of see where I live. This is Missoula, Montana. And here we have a whole array of solar panels. This again is photovoltaic, just so you don't get confused between solar thermal or passive solar. And we're going to talk a little bit today about how these things actually work. Okay, so to start out, sun hits the panels. This is the very basic, and then we're going to get a little bit more detailed. So the sun hits the panels, creates electricity. The electricity goes over here into an inverter box. Now, here's a question for you, and we're going to talk a little bit more about that. Electricity comes in two different types of currents. Does anybody want to tell me what those two currents are?
There you go.
Alternating.
That's one of them.
It's a direct.
Direct. You got it. You got to think of, and here's the trick, you guys. You got to think of one of the greatest rock bands of the 70s and 80s, AC/DC. Okay?
There you go.
Alternating current and direct current. I just totally dated and aged myself. Apologies. So, anyhow, so what this does is that this is coming into our system on a direct current. A lot of our appliances, this electricity is a direct current. A lot of our appliances run on an alternating current. And so what happens is it has to go through this inverter box before we can use it in our house. Once it does that, it goes into the control panel, then heads into all of our appliances, and we can use the sun's energy to run electricity in our house, whether it's the lights or the refrigerator or a hair dryer. There's lots of different ways that you can set this up as well, whether it's with a backup generator. You can be grid tied. Anybody want to tell me what grid tied means?
Tied to a grid.
Tied to a grid. Okay, very good. So anyhow, what that is obviously we have an electrical grid. That's how we all get energy, the power lines that are running to our house. Well, you can still be attached to those power lines and have a solar array on your house or on your business. And what that means is that, and it kind of depends on where you live, But when you are making extra energy, excessive energy that you don't need, it's going to feed the grid. And it's going to actually, you're going to actually be selling energy to the power company at that point. And then let's say it's the middle of the night and you just absolutely have to watch that next episode on Netflix and there's no sun out to produce that energy. Well, then you can be pulling from the grid as well. And so you can be buying electricity from the power company. I was recently talking with a really interesting professor from the University of Montana who has done a lot of climate change research. And one of his theories and one of his ideas is that in the future, when we talking about alternative energies, is that each house is going to be, and each business is going to be its own little power station. That we won't necessarily be relying on gigantic power stations around the world or in our area to produce this energy, but that we'll each be little generators that are generating enough energy for ourselves, and probably more than we can use, and so that will be going then into sort of a community pot, if you should say, of energy. So it's kind of an interesting thing to think about, that your house could actually be a power station in and of itself. All right, so next thing we need to know. When I'm talking about watt, what am I talking about? What is a watt?
What is a watt?
What is a
Joule
watt?
per second. Joule per second.
Okay, well, what is it? What does it do? Why do we have watts? What do they do?
Does it
It's a
measure
form of
power?
It's a form of what?
Energy.
It's how we measure energy. It's how we measure that. And so when we think about watts, we think about, and this is again, I'm going to date myself right here, but we have one of these old-fashioned light bulbs, the kind that don't have the little squigglies on that are not kind of round, circular squigglies. A CFL. This is not a compact fluorescent. This is an incandescent bulb, and they are very inefficient. Just to let you know, one of these, a typical way that back in my day, when there was, obviously like horses and buggies, we would use one of these 100-watt bulbs. So that would mean that for 1 hour, this was using 100 watts of electricity. Okay, and this is also what the electric company comes around and takes at your meter. They'll give you a reading in both, and usually in kilowatts. And so a kilowatt is just 1,000 watts. So if you think about that, how do you get to 1,000 watts? And what is that? So you could have that one light bulb running for 10 hours. That'll give you 1,000 watts. Or if you left 10 light bulbs on in your house for 1 hour, again, you would get up to 1 kilowatt of energy. And so you can see that it adds up relatively fast. And so usually what an electrical company will do is it will bill out by the kilowatt used. And so it's a good way, if you're ever interested, you can take a look at your bill and it'll tell you, a lot of times it'll even graph out how many kilowatts your house used per month. And so a lot of times we see this, that in the summer, and you guys, let me see, are you in New York? No, you're not in New York. You're in, where are you?
Pennsylvania.
Pennsylvania, that's right. I knew it was close. So Pennsylvania. So you're a lot like Montana. In the winter, there's probably not a ton of sun. Probably a little bit chilly. Maybe not, probably going to be using your energy, their heaters a lot more. You're going to use more energy in the wintertime than in the summertime. Now, one of the things that's a little bit different about Pennsylvania than Montana is that you have humidity in the summertime. We don't have any humidity in Montana. It's very, very dry. And because of that heat and that humidity, a lot of you probably have air conditioners in your house. Is that true? Like accurate assessment? Yes. Okay, so that's another big one that's going to draw energy. So what we see in Montana is a lot of use of kilowatts in the wintertime, not so much in the summertime. Yours might actually be a little bit more stable all the way across. All right, so remember, AC/DC. This is going to help remember alternating currents and direct currents. And they play, like I said, they play a pretty big role in the type of system that you have. All right, now I'm going to show you a solar panel right here. You scooch over to it. Okay, so this is a standard solar panel. And my explanation at the beginning was, solar panels are easy. The sun hits them, they make electricity, then it goes into your inverter. Does anybody know how it makes the electricity? Okay. Any guesses?
Could you repeat that?
Yes. Does anybody know how it makes energy?
The sun. There's little receptors that, you know, trigger off when sunlight hits them.
Okay, so you're not too far from it. It's actually not that complicated of technology. So what it is a solar panel is made of very, very thin sheets of silicon that are sliced extremely thin. Okay, they're like little wafers. What they do is we then put them together, and sometimes.
Please enter your conference ID.
Oh,
Press the
goodness.
pound key when complete.
I think Colorado is still trying to pop in with us. So what we'll have is you'll have all these layers, layer upon layer upon layer.
Okay, I think
Okay, wonderful. Hello, Pennsylvania New Group. Just to get you caught up here, my name is Allie Dupuy, and we're talking a little bit about solar energy today. So how many of you are familiar with the solar panel? Ever seen one before?
Yeah.
Yeah? Good. Anybody have one on their house?
No.
No. That is okay. So we're talking a little bit about how they work. And so the basic idea is that the sun is going to hit the solar panel. The solar panel is going to do some magic, and we'll talk about that magic in just a second. And then the energy from the solar panel, the electricity that's then generated, goes into an inverter, which takes it from a direct current into an alternating current into your house, which you can then use to go ahead and power all of your appliances. So what I have here is the solar panel. We're going to talk a little bit more about the magic part of the solar panel. Anybody want to take a guess as to how a solar panel actually operates?
Anybody?
What's the question?
I know him.
How does it work?
How does it work? Exactly. So that is the question. So let me tell you a little bit about it. So solar panels are what they are. They're very, very, very thin layers of silicon that are sliced using a very precise cutter to be very, very thin. They're then stacked together. Now, what we do is we do something called doping. And just like you might think about doping when you think of Lance Armstrong, we do something similar with solar panels. We put an impurity into them. Now, silicon is a very stable element, very stable. And one of the reasons why it's so stable makes it a great candidate for this. But also, we can't have quite the stability that we needed. So, if we're thinking about an atom, we have the atom, and then in the center we have the what, everybody? Nucleus. And there's also something that is right around the nucleus, which is the proton. Very good. And then we have something that's orbiting, sort of like the Earth is orbiting the sun, and those are electrons. Exactly. So we have the nucleus, then we have and the proton, and we have the electrons. Now, electrons are negatively charged. Now, this is okay. Going back to your chemistry classes. Tell me, how do the electrons like to be together, or do they like to be separate? What's their favorite state?
Separate?
They don't. They like to be together. They like to have a pair. They like to have a buddy. The most stable elements, all the electrons are going to be paired up. And so what happens? What happens if they are not paired up? What are they going to do? Back to chemistry, you guys. Chemistry 101.
Not good at chemistry.
You're not good at chemistry. It's okay. Colorado, do you want to tell us what do atoms do if they're kind of unstable? They have electrons and coming around, and that electron is by itself. What is it going to do?
Boy, seventh period was on call.
It's gonna try and find a friend. Okay, it's going to try to match up with another electron. Now let's think about, that's why we get water, like H2O. We have an unstable element. They're going together. They're connecting. They're creating water. So same thing. So we've now doped our silicon, so we have an unstable element. That means that we have extra electrons kind of flying around there. And kind of wobbly. So here's what happens. The sun hits these panels. When it hits those panels, those electrons are activated. They start spinning around. They start looking for a friend, if you may. And so before they can really find a friend, because it's continuously sunning, the sun keeps hitting the solar panel. Now, when electrons are spinning around, what is being created?
Energy.
Electricity. Electricity is being created. So what happens is that we start to get a current. We start to get an electrical current. And so as the sun hits, it's causing those electrons to go scattering everywhere, looking for a buddy, looking for a friend to meet up with. And what's happening is you can see these little silver lines. Well, in each of these black squares, these black rectangles, there are also little teeny tiny silver lines. What those are conductors. It's going to conduct, it's going to gather that energy, and it's going to send them to these larger lines, which is going to send them over to the end of the solar panel. At which point, we can gather all of that energy and all of that electricity, and your solar panel is then creating the electricity that goes into the inverter and then into your house. Can you use a solar panel directly without an inverter?
No.
You actually can. You actually can.
Yeah,
So,
very good.
you can't. So not everything runs on an alternating current. In fact, a lot of our appliances, probably a lot of our phones, things like that, don't require that. In fact, you can turn it over and you can see how many volts, how many amps are required to run run that machine. As long as it doesn't run on an alternating current, you can go directly into it. Another thing that you can do is you can make your solar panel go directly to like a generator, a battery that will then later be accessed through the house. So you can store all of your energy into a battery from the sun, and these are just different setups that one might use. If you're building a cabin in the far reaches of Montana where there's no grid to tie into, and so we talked a little bit earlier about a grid tie. What a grid tie is when there's the electrical grid are the power lines, or everything that's the way that the power company gets energy to your house. When you're grid tied, that means you are receiving energy from the house. Now, if you have a solar array on your roof and you're creating extra energy, what happens is that energy is essentially sold back to the power company. And so you are generating more energy and you are selling your energy that you're making back to the power company. And so that's grid tie. But let's say that we don't have, and one of the advantages is say in the middle of the night you are really dying to watch that next episode of Game of Thrones on Netflix, and so there's no sun outside, but you still want to do it, so you use the energy from the grid, okay? Now, if you're using a battery, you can store all of that energy, and you can grab the sun and you can store it into the battery, and then you have a set amount of energy that you're going to be using, as much as that battery will hold. And so then you have to kind of be a little bit more careful and think about, okay, do I have enough energy to dry my hair, watch Game of Thrones, and charge my cell phone? And so you have to start thinking about things a little bit in that nature. But if you live in a place like the outreaches of Montana, in a little tiny cabin where there's not a lot of power lines, then that could be a really good option for you. Okay, does anybody have any questions about how the solar panel actually creates electricity?
No, thank you.
No? How about you, Colorado? Do you have any questions?
Colorado.
Wow.
You guys, let me introduce you. Colorado, Pennsylvania, Colorado. Welcome.
Colorado.
So I actually have a question for Colorado, because I talked to one of your teachers this morning, and I discovered that you are a mountain town that's at about 10,000 feet elevation. Is that correct?
Yeah.
Yeah. We're only half of that here in Missoula, not even half of it. So do you guys see a lot of solar applications in where you live? Do you guys see any solar panels?
Absolutely.
Very
Here's on
cool. Another question is, do you have any on your school?
Oh, yeah.
Again?
Do you have solar on your school? No? Okay. We'll go ahead and keep moving on. So, I told you this time. We talked a little about the solar panel.
Quiet.
On here. All right. So, when you're thinking about installing solar panels, there's a few things that you have to think about. So, one, we have temperature. Because as we're going to find out in just a few minutes, there is a temperature that works best for solar panels. So temperature is definitely one of the things. Shading. Do you get enough sunshine? Where I live, we have a lot of mountains, as Colorado might as well. Pennsylvania, you might not have that much of a problem, but it is an issue sometimes where mountains or trees will shade you. Another thing that we often have is very overcast. I live in a place that has extremely overcast skies in the winter months, and so maybe solar isn't the right option depending on where you live. So we have to sort of think about this. We have to sort of think about solar radiation, which is how much of the sun's energy is actually being directed to that spot. Okay, so here's a really fun little gadget, and this is called a solar pathfinder. And what it is it has some highly reflective glass on it. That is it's a half circle shape. And underneath it, you'll see these lines. Anybody want to tell me what we're measuring here? Any guesses? Colorado, what do you think we're measuring? What are we looking at here?
Can you even hear us? Can you hear
I
us?
can hear you a little bit, but not very. I can hear when you speak, but I'm not sure if when the students are saying.
Okay.
Yeah.
What are they measuring? They don't know.
We know.
So, you don't know. We're mapping something. We're mapping some Pennsylvania. Do you know? What are we measuring here? What are we looking at here? What are we trying to graph?
What are the units for it, Lumen?
All right. So I'll show you. So this is actually very, very cool. What we're looking at is we are looking at where the sun is going to be on the horizon and how much solar energy we will be able to get from a spot. So if I have, let's say that this is where I'm going to build my house, right here in this spot, and I am going to, according to my plans and the specs, this is where on top of my house the solar panels are going to be. Now I can take a look at this, and you can see, I can take a look and I can go around, and I can see that, okay, if this is my house, and these trees might pose some problems during the month of August. Or this is a very good picture. We're not seeing a lot of trouble with it, but what it does is it's going to tell us, based on the sun's angle in the sky, the angle of incidence, how much energy we're going to be receiving, and whether or not we need to choose a different site for our solar panels or not. So it's a very handy tool for when we're assessing a solar site. So then we think about, so I said this thing, the angle of incidence. Does anybody know what the angle of incidence is? It's not just with solar. Airplanes use angle of incidence. What is that?
The angle in which the light, which is the first angle, it's the first angle.
It's the first one. Okay, it's when something is hitting something at an angle. Okay, basically that's like the very, very basic of it. So with an airplane, the angle of incidence would be the wind hitting the airplane wings to provide lift for the airplane to go up in the air. Okay, when we're talking about solar and the angle of incidence, we're looking at how many of those rays, how can we get the best possible amount, or the most of the sun's radiation to hit that solar panel so that we have the most efficient solar panel. So one of the things that we discover is that if it is perpendicular to the sun, we are going to have the most rays hit that solar panel. If we tilt it a little bit, you'll see that some of those rays are missed. If we tilt it even more, we miss more rays. Now, is this ever going to change during the course of the summer or the winter?
Yes.
It is, and we can look down here. Here's our summer sun path, and here's our winter sun path. Especially in places further north, we're gonna have longer days. We're gonna have a lower sun in the wintertime. We're gonna have a higher sun in the summertime, and that's absolutely going to affect it. So to place a solar panel, and okay, here's another question: if we place a solar panel perfectly flat on the house, is that the best angle of incidence?
No.
No, because when is the sun directly overhead?
Just a bit past midday.
But it's probably directly overhead with the perpendicular on June 21st, on the summer solstice at 12 o'clock. So that one day would be the best day to have your solar panel be flat. So what we do is, one of the things we have to do is we have to calculate and we have to figure out, based on the latitude at which you live, what the angle for the solar panel is and what the best one is going to be. Now there are solar panels that track the sun, and of course those are going to be much more efficient because they're always giving you the best angle and they're following the sun so that you're always getting the most rays. This is another crazy chart and a way to look at the solar panels, or to look at the latitude. So we can find, this is at latitude 50, which is very, very close to where we are. We're about 46 degrees north. And you can take a look and you can find it based on what time of day, what season, where the sun is going to be. And so this is a very helpful chart. This is the chart that does what that little solar finder will do. So there's multiple ways to find it. And then we're also we can also resource charts that are going to tell us sort of how much solar energy is going to be hitting our place, because it's going to vary. Where is there the most in the United States?
Southwest.
Yeah, Southwest over here, exactly. So let's see. So Colorado looks like a pretty awesome spot for solar energy. Montana's got some okay spots. It's also got some spots that might not be the very best. Interesting thing. So up in this area is rainforest, as along with over here. You can imagine that a rainforest might not be the best place to have solar energy. Why would that be?
What?
Yeah, it's raining. It's cloudy. Exactly. Over in this area, you're doing pretty well. I'd say the lower parts of the states are going to have a little bit, or the more southern parts of some of those northern states will have a little bit better solar energy. But at the same point, it's still energy, and it's still being made, and it's still helping to reduce other energies that we're using. Okay, so I'm just going to take you through what it looks like to set up a solar array. So this was done on a school in Missoula, Montana just recently. First thing they had to do, and we worked with a group of students who helped plan out everything and were really involved in the whole process. So one of the things that we had to do was figure out how much energy the school was using, how much money they had for solar panels, and how much energy those solar panels were then going to cover, and how that fit into the whole plan. So that was the first thing. So that would tell us kind of how many solar panels we could get. The next thing we had to do is we had to find the layout. Which direction are they going to face? Anybody want to tell me what is sort of the go-to direction? North, south, east, west. You have 4 guesses. Colorado, what do you think? I'm going to put my solar panel. That's right. Yep, I want it south. It's right. South, southeast is kind of where we're going. Usually that'll give us the most exposure. Things on the north, if you think about that, then you think about the clothing company, the North Face. They're called the North Face because they're cold and they're rugged. North side of things is going to have less sunshine. The south is always going to have more sunshine. Okay, so they have it set up. So then they head up to the roof. Heading up to the roof, and they gotta lay it out. You have to do a layout. You want to make sure that everything is going to be in the right places. So you're using it's like pretty expensive equipment, and so you want to make sure you get it done right the first time. So you lay it out. I'm not going to show this with you right now, but I will send this to you. It's this load chart, and what you can actually do with this is you can take this and you can go through your school or your house, and you can figure out the different loads, and then you can compare it to find out how much energy you could potentially save or use via solar panels. So it's a very interesting, very helpful chart, and it's something that we use quite frequently. Okay, so then we got to set everything out. We got to get everything just so. We're laying it out. These are the brackets, the bracing for the solar panels. They're pretty heavy. It's a pretty big piece of equipment that we're using, and so you want to make sure, like I said, it's done right. See, the guy's got his T-square here, making sure everything is level and straight. And if it's not, we just saw about when we were talking about the angle of incidence, if you have things off, even by a couple of degrees, it can really affect the efficiency of those solar panels. So we're going through, this is the setup. So this is a mounting bracket right here. And this is where, as we go and start seeing, they come more mounting brackets. This is where each of the solar panels are going to be installed. So putting some down, getting them ready. The grid, as you can see, there's now a grid that's sort of laid out. We have to add blocks. The blocks are going to help us put them up and angle them the right direction. They're also very heavy, and they're going to make sure they're going to act as sort of a double safety. If you notice that everything is screwed down, it can get windy. The tops of buildings can be kind of a crazy place, and so this acts also as just like a secondary security blanket there. Running electricity to it, or I should say from it, because this is where the electricity is going to be going from to the school. So running that, it's got to go through all the different areas down to the schools, ultimately to the school's power box. And the school does have an inverter so that they'll be able to use it, so that their computers will be able to run on it. They believe that most of this is going to be generated towards their computer lab. Okay, so then they're putting the solar panels on, and actually what you're seeing is a bunch of our high school students up there on the roof actually doing the install with the solar company. So putting them on, you can see they're at about a 45-degree angle. That's about, in Montana, that's about the angle that you want your solar panels to be at. Putting them together, they're connecting the wires. It's kind of like when the magic starts to happen. There we go. We have the full array of solar panels. So pretty fun. Now I want to show you something, and this is actually kind of one of my favorite things about energy and solar energy. It's not the actual putting in, but it's the watching it after. Does anybody want to tell me what we're looking at right now? Any guesses? It's a graph, yeah. What's it a graph of?
Solar intensity.
So I actually have a solar array on the top of our studio. And this is a 24-hour peak at what has happened with the sun and the solar. This is a way to measure and to monitor. And so a lot of things that places do is they monitor, and it gets a lot of information. So just looking at this, what can you tell me about this graph? What has been happening with the sunshine? Has there been a lot of sunshine?
No.
Not a lot. No, not at all. In fact, you can see here where this line is. What we have right here is this is energy that we're using excessively. So this is stuff. And then when we have it over here in the green, I'll scooch over to this side. So we have the green over here. What I'm showing you right now is this is when we're actually producing more energy than we're using. And so if it was kind of at the same, if everything was right there at the same line, that'd be what about what we're using. So let's take a look at this, and then, okay, then this is one of my favorite things, because you can actually see what is going on right now. Can everybody see that? Is that off the screen for anybody?
Kind of.
Let me move it over just a little bit, because it is kind of fun to watch, because it's real time. Is that better?
Yeah.
Okay, perfect. So that's real time. That's what's actually happening right now. We are producing almost just under 2 kilowatts of energy, and we're currently using 820 watts. So you can see that we are producing more than we're using right now. So that's really good. Let's take a look at what if we went to, I'm going to go 6 months, because that should give us some summertime readings as well. So, whoa, I know, right? Pretty intense. So we have a lot of energy that's coming out of here, and so you can see that most of the year, I bet on average about half of our energy is produced using solar panels, and the other half, maybe a little more at times, maybe a little less at times, the other half is used on the grid and is grid tied. So it's energy that we're getting from the grid. So we can also look at this and see what this is. And so at the peak, at the ultimate peak, we're using about 4 kilowatts per hour. And you can see that these are set up a little bit challenging. So this would probably be more like 4 kilowatts each of these little spikes is like a day. It's like the average for the day. So on this day, back in October of 2013, we were actually using pretty much 4 kilowatts steady per hour that day. So that's quite a bit of energy. If we go back, I just want to take a look at the year. It'll be even crazier. But that gives you a really interesting idea. And you can also see where the spikes are. One of the things that we noticed for a while is that we had a spike that was happening that we couldn't identify. And one of the things that we discovered is that something was broken in our we have a big shop next door that runs a lot of power tools. It was broken, and there was something that was running constantly. I want to say maybe it was a compressor, but it was constantly running and it wasn't shutting off the way it was supposed to, and it was using a lot of energy. We were able to look at that and we were able to discover that something's wrong, something's amiss, and we can see it by what energy we're using. You get to know these pretty well, and you get to be pretty familiar with your own setup, and you can look at it and you can say, okay, I know what this spike is. This spike is when we have this appliance running, or we're running these electrical tools. I know that we're going to have a huge spike in electricity. Other times, you can look at it and say, okay, well, maybe we weren't very busy at this point in December, January. It wasn't a time where we needed to use those, so we have less energy that's being used. In a school setting, it's very interesting. Okay, so here, this is the other way. We're going back to an hour. We can look at this and we can say, okay, well, what's happening within this hour? And you can look at these, you can kind of micromanage these, and you can look at it and you go, okay, well, this guy right here is about the same height as that guy, which is probably included in that guy, which is about every 15 minutes or so. That's the refrigerator coming on, the small fridge that we have that's coming on, that's creating the energy, that's just cooling it down. It cycles about every 15 minutes. And so you can start to identify those different things, and you can see what's happening. So when we're talking about energy conservation, which is a very important piece of this, because if you're going to have a solar array, you don't want to be spending extra money on extra energy that you don't really need. You start to look at this and you start to figure out, how can I save energy? Or what am I doing? Or why is this little blip there? Why is this little bump there? Have any of you ever seen any software like this before?
No.
It's pretty interesting. Based on what we're looking at today, so oh my, what just happened? What just happened with the weather?
It got hotter.
Cloudy.
It got cloudy.
So a couple of things happened. So this is a spike in our energy usage, and this right here is a spike in our production. So what this is telling me is that it's kind of overcast today. It's coming in and out. There's the sun's shining. There's a few high clouds that are up there. So what's happening as the sun shines down, we're going to have a higher usage, more energy that's being produced. As it gets clouded, there's going to be less, and so you'll see that variation throughout the day, and that'll play a big role also in sort of those green lines as to where they are working. Okay, so somebody said temperature. I have a little math problem for you guys. Anybody want to try?
Yeah.
Yay! Okay, so temperature actually plays quite a role in the efficiency of solar panels. Does anybody want to take a guess off the top of their head what is more efficient? Heat or cold? If a solar panel is in a hot area or a cold area, what is more efficient? We're gonna be
Colorado.
okay. So heat. Yep. Okay. So it's actually cold, which is kind of goofy. I'm gonna switch over here. I'm gonna switch over views. Volt times an amp equals a watt. Okay. And those are kind of important things to remember. So voltage is higher in cold temperatures and is lower in warm temperatures. So it's kind of funny. I always thought that that's a little backwards in my mind, but that's how it works. So we can make this into a calculation. So voltage is going to vary 1/2 of 1 degree for every degree of Celsius in temperature change. So we refer to temperature change as delta T. Does this look familiar to anybody? Has anybody ever talked to them about? Yes, I'm so great. So let's say that our solar panel right here, here it is, it's producing sunshine, it's great, and this is our average 12-volt solar panel, okay? So what that means is that we're, when we're running kind of on average, we're going to be, it's 12 volts that it's rated at, or also be rated at 80 watts. So ultimately, it would be producing 80 watts of energy with a high voltage of 12. So what we're going to do, one other point, this is at 25 degrees Celsius. And so 25 degrees Celsius is going to be our baseline. So what we're going to do is we're going to take 17.1 times 4.68, this is our volts, amps, we have 25 degrees. So this is our information. This is our base information here that we all need in order to create this program. So let's just say that instead of our temperature being 25 degrees, it is negative 20 degrees Celsius outside. So what we want to find out is what's going to be the new efficiency of our solar panel. So the first thing we have to do is we have to take the delta T, the temperature change, between 25 degrees Celsius and negative 20 degrees Celsius. And the delta T is, does anyone want to tell me?
45.
Good job, 45 degrees Celsius. Excellent, or it's 45 degrees, yeah. So our it's actually delta T like this. So our change in temperature is 45. Okay, so what we're going to do is we're going to take a 0.5%, so we're going to do 0.005 times our delta T, 45, and that's going to equal 2.25 or 22.5%. Okay, now what we're going to do is we're going to throw this into the equation that we had up here. So we're going to take volts. We're going to take our volts and we're going to go, if we have volts times amps equals watts, we're going to go 0.225. I'm going to do a piece of paper here so you can see. We're going to go 0.225 times 17.1, and this is going to give us our volts. And what we get is 3.85 volts. So what we're doing here is we're taking this equation and we are finding what the difference is. So if we have now taken 1% of 1 degree, what does that equate to for our volts? So then we're going to go, it's going to give us 3.85 volts plus our 17.1 volts. So you might be asking, where is the 17.1 volts coming from? Because a panel is rated 18 volts, it's actually 17.1 volts, and that's kind of where that's coming from. That's a little confusing, and I apologize I didn't say that at the beginning. So what we get, 3.8 plus 17.1, comes out to 20.95 volts. Now, if we have 20.95 times our amps, and our amps in this solar panel is 4.68, we're going to get 98 watts. So at negative 20 degrees Celsius, our panel is producing 98 watts of electricity. Now this is Now this is a panel that is rated on average at 80 watts. So the colder it is, the higher this is going to go. The lower this number is, so the warmer it is, it's going to go the opposite direction. So we have 18 watts of efficiency increase based on this formula. So it's kind of interesting. It's something that we look at, especially when we live in cold places like Montana and Pennsylvania and Colorado, where half of the winter time we are not actually in sunshine and lovely warm weather, but we are in a place that is going to be cold, and we can use that to our advantage. We also need to look at that during the winter time, during the summertime, when that efficiency is going to go down. And so all of that's going to do is all of that is going to help us determine how many panels we need where we need to put those panels, and how those panels are going to work for us. Does anybody have any last questions? Oh, and I've got another call coming in. Does anybody have any last questions about solar energy before we go today?
Oh, we missed the first
How much
half.
does a solar panel cost?
Good question. So it varies greatly based on what the solar panel is rated. It also varies on what types of grants are available for you. You can get a setup for between probably 15 and 20 grand. Okay, it's kind of a lot. That's more than one solar panel. That's enough to probably do a 2 kilowatt array or I'm sorry, not a 2 kilowatt array. 1 kilowatt, and that's usually with some help from local subsidies. So a lot of times, energy companies will offer grants and assistance and programs where you can buy solar panels and you get like a mail-in rebate sort of when you put alternative energies on your house. So it varies greatly. It varies greatly based on the materials that are used to build them, where they're built, who built them. Just like many other things, there's quite a variation. So it's expensive, but if you use the right resources, you can bring that number down quite a bit.
Okay.
Well, we appreciate it.
All right. Well, thank you guys so much. In Colorado, I'm sorry you had a hard time connecting this morning, but I'm glad that you guys are here now, and I will send you a little bit more information on some of the parts that you missed.
Great. Thank you so much.
All right. Thanks, everybody.
Thanks,
Have a
Allie.
wonderful day.
See you,
Bye.
Colorado.